This is problem A, and I call this the ski lift. And I just restarted figuring out how I write on this tablet, so my handwriting might not be the greatest. And it says a 75.0 kilogram skier rides a 2,830 meter long lift to the top of a mountain. The lift makes an angle of 14.6 degrees with the horizontal. What is the change in the skier's gravitational potential energy? So first I'm going to make a drawing. And yeah, this will be fine here. So there is the distance, and here is 14.6 degrees. So 14 was supposed to be a 14.6 degrees, and then this one here is 2,830 meters, and I guess here's the skier. There we go. And then what we're supposed to figure out is what is the change in the skier's gravitational potential energy. That means that the skier down here starts with a certain initial potential energy, PE0, and then here with a certain final potential energy, PEF, and all that depends on is the height h, this one here, that the skier is being lifted. Okay, so what we have to calculate then is potential energy equals mass times gravity times height, and the height is according to the sine of the angle. So h equals, I'm going to write this on the side here, h equals the distance d, there we go, distance d, d times the sine of the angle. Okay, then I actually kind of forgot something. We then there's actually start filling out this table here, and we have given the mass of the skier to be 75.0 kilograms, and so now here in inside I'm making it more proper that I have the mass given, that of course acceleration due to gravity is given, and I'm supposed to figure out what the potential energy is, and with the distance being given, I can figure out what the height is, and therefore I can figure out what the potential energy is. Notice I also have the distance d given. I think I'm going to make a check mark there. However, I don't have the force given here. I could call it the gravitational force, but that almost makes it too complicated. So if I had the force here, I would come up with an amount of work which would equal the potential energy. In any case, when I plug in the numbers, so the result is going to be, therefore, 75.0 kilograms times 9.8 meters per second squared times the height, which itself is 2,830 times meters times the sine of 14.6 degrees, and you're going to come up with units of kilograms. I'm going to write this here down here, kilograms times meters per second squared times meters. So mass times acceleration times height, that's kilograms meters squared per second squared, which is in standard units. So we have an abbreviation for that, and you're going to come up with joules. This I call problem B, and that is apparently about a gymnast, as you can see from the drawing. And it says that a gymnast is swinging on a high bar. The distance between his waist and the bar is 1.1 meters, as the drawing shows. At the top of the swing, his speed is momentarily 0. Ignoring friction and treating the gymnast as if it as if all his mass is located at his waist. Find his speed at the bottom of the swing. So I had to pause in between to make sure that actually my microphone is on. So up here the velocity is 0, and of course I would call it the initial velocity, 0 meters per second, and then they want to figure out what the velocity is down here, Vf, and then that comment about the mass being concentrated at the waist means that from here to here is what you would have to calculate. So the change of the height of the mass goes from here to here, and that of course is twice the radius, so it goes down by 2.2 meters, and of course I may want to call that the difference in height is 2.2 meters. Sorry that my equation signs don't look very good, but that's again because I'm still practicing on this tablet here. Okay, in any case, what we have given here is V0, what we have given is Vf, what we have given is the height h, and of course what's always implied is the acceleration due to gravity. Okay, notice that we actually don't have given the mass of the gymnast. I don't remember having this one here, so that's kind of interesting, but we'll see what happens. Any case, the way we should attack this problem is that up here we have potential energy. So potential energy on the top, and no kinetic energy at the top because the velocity is 0, and then at the bottom we have kinetic energy because the gymnast will be rotating through here, so he will have some tangential velocity, so kinetic energy. And now you could argue that the gymnast is also above the floor, which means he does have potential energy, and he would notice that if he falls down here, the butt is going to hurt simply because he fell from a certain distance, from a certain height. However, you will see this in the book, and I point this out here, at least I hope you will see it in the book, at least I point it out here, is that for potential energy you can choose the 0 level to your convenience, which means that you can choose it here at the floor. This is where potential energy is 0, or you can choose it here at the waistline where he is at the bottom. This one in this case here is convenient because if I choose this one 0, then I just have to calculate the potential energy with 2.2 meters up. Notice that they don't actually tell us how far above the floor is the waist, and therefore this 0 level potential energy becomes inconvenient, and that's why I said let's choose the other one. So here we would choose this one here conveniently to be potential energy equals 0, and that's why at the bottom that looks like a little bit better of a equal sign, equation sign. So I have 0 joules at the bottom where the waistline is when he swings through here. Okay. Still, I don't have the mass. Let's see what's going to happen. So at the top it's mass times gravity times height, and at the bottom it's 1/2 times mass, and you can see already what will happen, velocity squared, and I should call this Vf here squared. Notice that VO squared doesn't show up here. It should be on the left hand side, but we already know it's 0, so I could write it in there. I don't have to because it's already 0. Okay, let's see. Yeah, that means now that the mass divides out. There we go. And so overall, actually, we didn't need the mass. I'm going to make a cross here that you will see this in other problems where they don't give us the mass. It doesn't matter what mass it is. So if you have a 50 kilogram gymnast or if you have an 80 kilogram gymnast, either one of them is going to swing through with the same velocity at the bottom because it does not depend on the mass of the gymnast. Okay, I'm supposed to